Hello, Year 9. So recently we've been talking about chemical reactions. And as you know, chemical reactions are where atoms can rearrange to form new substances. However, nothing actually happens or changes within the individual atom itself, where nuclear reactions actually undergo a change of the center of an atom. So if we remember what an atom looks like, it has electrons that go around the nucleus. Now, the nucleus contains the protons and the neutrons, and also that is where all the mass occurs. Okay, so today we're going to look at exactly what happens in regards to a nuclear reaction. Okay, basically, if you were to take an element such as a sodium atom, okay, the general term for an atom changing or converting into another element is known as transmutation. So here's an example: sodium atom. It can actually change into a neon atom. Okay, we say it's transmutated by nuclear reactions. Okay, it undergoes what's known as nuclear decay, where particles actually come out of the nucleus and are emitted out of the nucleus, and it changes the whole makeup of the atom. Okay. Most elements, okay, and most atoms are actually stable, but some, including the nuclear atoms, are actually not stable. Okay, we'd say they are unstable. They're also known as radioisotopes. Okay, the reason they're known as isotopes is because they have the same number of protons. Remember, the protons are in the middle, and a different number of neutrons. So if the protons were the blue, the neutrons would be the red. Okay, and those are known as radioisotopes. Okay, so here's an example of an isotope. Here you've got carbon-12. Okay, that can change into carbon-13 and carbon-14 molecules or atoms, sorry. And these atoms are actually also in your body and decay over time. In fact, the whole way that we can date organic matter is looking into the isotopes of carbon-14 and looking at the ratios of the carbon-14, which are very rare in your body compared to the carbon-13 and carbon-12 atoms. Okay, so the three types of decay that we're going to talk about are alpha, beta, and gamma decay. And remember, these are all particles or waves that are emitted from the center of an atom. All right, so looking first of all at alpha decay, that's the first symbol of the Greek alphabet. Okay, it looks a bit like an A. What alpha decay is basically a relatively large particle compared to the other particles being emitted from the atom. If this is my atom here, I'll turn it on its side so you can see it. I've actually made an alpha particle. And an alpha particle basically contains two protons or positive particles, which are the blue ones, and two neutrons, which are the yellow particles. Okay, so if you imagine this is just an atom, the atom is emitting alpha particles. Now, because alpha particles are quite big, it means that the atoms that emit them are also a lot bigger. They are atoms such as uranium, for example, would emit an alpha particle. Alpha particles have been considered to be very, very similar to an helium atom. Okay, so for example, that's a helium atom on the right. An alpha particle there is very similar. It has two neutrons, two protons, and a mass number of 4 and 2 electrons. Okay, so the next particle we're going to look at is known as a beta particle. Okay, here's a beta particle here, and a beta particle is a lot smaller. In fact, it's very similar to an electron. Okay, it has a negative charge. It basically doesn't weigh anything, just like an electron weighs very little. And what happens in beta decay is that a neutron actually converts to a proton, and that starts to change the atomic number. If you remember, the atomic numbers are the numbers on the periodic table that go consecutively, 1 to 118. If those electron numbers change, the actual element changes itself, okay? So here you can see a carbon atom is actually changing to a nitrogen atom because of the beta particle or the electron that is being emitted. Okay, the mass number, the 14, which is the mass of the nucleus, stays the same, but because of the beta particle, it's actually changing into a new element, okay? The last part of decay we're going to talk about is known as gamma decay. Now, gamma decay is a type of decay you don't want to go anywhere near. It's dangerous. It's like a very powerful X-ray, and instead of being a particle, it is actually a wave, okay? So it moves around just like other waves do in the electromagnetic spectrum. Basically, it's a wave of energy. It's at the speed of light. If an alpha particle was to travel at, say, 10% of the speed of light, and a beta particle traveled at 90%, well, a gamma particle would travel the whole way, 100% of the speed of light. Okay, so that's an example of a parent nucleus actually changing to a daughter nucleus there. Okay, and finally, the penetration of radioactive particles. The particles basically penetrate different materials in different ways. Okay, so an alpha particle, for example, wouldn't even be big enough to go through a piece of paper. So if this is my alpha particle here, this is my piece of paper, it's going to get blocked by the piece of paper. Okay, a beta particle, on the other hand, is a lot smaller, it's a lot faster, it's like an electron, it can get through the piece of paper, okay, just like that. And but it actually stops at aluminium, okay? But a gamma particle, as you can see there, can get through paper and aluminium. It's that small. In fact, the only thing that can really stop it is very dense particles, one being dense enough, which is lead, okay? So imagine this is a block of lead, then this gamma particle would not be able to get through lead, but it would be able to get through the paper. It would be able to get through the aluminium, which is my hand in this instance, okay, but not through the lead. All right, let's just have a little revision quiz. So I want you to pause your computer screens at this point and have a go at these 7 questions, and we are going to go through these questions in class. Okay, well, I hope you have enjoyed today's lecture, and I will be seeing you all soon.